As we discussed some properties of irrational numbers in the chapter Real Numbers of class 10. Now we continue the problems on irrational numbers. Today we have to show that square root of a prime number is an irrational number. If we prove this, we can show that square root of p plus square root of q is a prime number where p and q are prime numbers. Similarly, we can solve some different properties of irrational numbers in today's class. Let us start our discussion. Class 10 real numbers. Students, you can refer the pages, page number 16. Page number 16, exercise 1.4. Exercise 1.4. The first problem. Prove that square root of 3 plus square root of 7 is an irrational number. To prove this result, we follow contradiction method. To prove that square root of 3 plus square root of 7 is irrational, we follow contradiction method. In contradiction method, we assume that the given statement is not true. That is, we assume that square root of 3 plus square root of 5, square root of 7, square root of 3 plus square root of 7 is not irrational. In the sense, we assume that square root of 3 plus square root of 7 is a rational number, is a rational number such that so when we define a rational number, we have to write the conditions such that square root of 3 plus square root of 7 equal to a by b, where first condition, a and b are integers, a and b are integers, b is not equal to 0. This is the first condition. Now the second condition is a and b are co-primes. The second condition is a and b are co-primes. What is the definition of co-primes? If the highest common factor of two numbers, two positive integers is 1, then we say that they are co-primes. So we write it highest common factor of a and b equal to 1. So here we have defined a rational number of the form a by b. That is, we assumed that square root of 3 plus square root of 7 is a rational number a by b with condition 1 and condition 2. Now we rewrite this square root of square root of 3 equal to a by b minus square root of 7. Squaring on both sides, squaring on both sides, we get to square on both sides, we use the formula x minus y whole square equal to x minus y whole square equal to x square plus y square minus 2xy. We use this formula to find the square of the right hand side. Square root of 3 whole square equal to a by b minus square root of 7 whole square. Square root of 3 whole square is equal to 3. This is equal to a by b whole square plus square root of 7 whole square minus 2 multiplied by a by b multiplied by square root of 7. This is equal to a square by b square plus 7 minus 2 root 7 a by b. This is 3 equal to. Now multiplying both sides by b square. Multiplying both sides by b square. We get 3b square equal to a square by b square multiplied by b square plus 7b square minus 2 root 7 a by b multiplied by b square. This is equal to a square plus 7b square minus 2 root 7 AB. So I write the left hand side 3b square. 3b square equal to a square plus 7b square minus 2 root 7 AB. Now I would like to bring this term to the left hand side and 3b square to the right hand side, so that I get 2 square root of 7 AB equal to a square plus 7b square minus 3b square. This is equal to square root of 7 multiplied by 2ab equal to a square plus 7b square minus 4b square. 7b square minus 4b square is 3b square is 4b square. So square root of 7 equal to a square plus 4b square by 2ab. Now we got this. So we got square root of a square plus 4b square divided by 2ab equal to square root of 7. A square plus 4b square by 2ab equal to square root of 7. Now we consider the right hand side terms. A is an integer, B is an integer. This implies that a square is an integer and b square is also an integer. That is, the product of two integers is again an integer. So a multiplied by a is an integer, b multiplied by b is an integer. So from this, I can write a square is an integer. From b square, I can write 4b square is an integer. Why? Because 4 is also an integer. So 4 is an integer, b square is an integer. So the product 4b square is also an integer. Now from this we get if a square is an integer and 4b square is an integer, the sum is also is an integer. The sum of two integers is also an integer. Now we write a square plus 4b square is also an integer. This is also an integer. We got this. Now we have a is an integer, b is an integer, b not equal to 0, and highest common factor of a comma b equal to 1. So all this implies that a is not equal to 0. When the highest common factor of two integers is 1, then a cannot be equal to 0. Now we write the step a is an integer, b is an integer, 2 is an integer, implies that 2ab is also an integer. 2ab is also an integer. And since a is not equal to 0, b is not equal to 0, and 2 is not equal to 0, we get that 2ab is not equal to 0. So from this we got a square plus 4b square is an integer and 2ab is also integer and it is not equal to 0. So we can conclude that hence hence a square plus 4b square is an integer, 2ab is an integer, and 2ab not equal to 0 implies that implies a square plus 4b square by 2ab is a rational number. It is a rational number. That means the right hand side term of square root of 7 equal to, we have square root of 7 equal to a square plus 4b square by 2ab. We have this statement. Square root of 7 equal to a square plus 4b square by 2ab. Now we proved that a square plus 4b square by 2ab, that is the right hand side term, is a rational number. When the right hand side term is a rational number, we can conclude that the left hand side term square root of 7 is also a rational number. So now we write so this implies square root of 7 is a rational number. But we have already proved that square root of 7 is an irrational number. So this is a contradiction to the fact that square root of 7 is an irrational number. Now we write that step. But we know that square root of 7 is an irrational number. It is an irrational number. We have already proved this. We proved this statement. Square root of 7 is an irrational number. So we got the contradiction. We got a contradiction. We got a contradiction to the fact that square root of 7 is an irrational number. So why we got contradiction? This contradiction has arisen because of our wrong assumption that square root of 3 plus square root of 7 is a rational number. Hence, our assumption is wrong. So now we write that. Hence, our assumption our assumption that square root of 3 plus square root of 7 is a rational number is wrong. So this statement is wrong. So we can conclude that the square root of 3 plus square root of 7 is not a rational number. Therefore, square root of 3 plus square root of 7 is not a rational number. If this is not a rational number, then it must be an irrational number. That is, we write now the definition of an irrational number. A real number which is not a rational number is called an irrational. Now we write this step. A real number which is not a rational, which is not a rational number, is called an irrational number. Hence, we conclude that hence square root of 3 plus square root of 7 is an irrational number, is an irrational number. So we proved this by contradiction method. We proved this result by contradiction method. Dear students, I would like to explain this briefly. Prove that square root of 3 plus square root of 7 is an irrational number. This is the given problem. To prove this result, we consider the contradiction method. By contradiction method, we assume that the given statement is not true. If the given statement is not true, then it square root of 3 plus square root of 7 is not a irrational number. We assume that square root of 3 plus square root of 7 is not an irrational number. If this is not an irrational number, then it must be a rational number. So we assume that square root of 3 plus square root of 7 is a rational number satisfying the conditions number 1, a and b are integers. A and b are integers where b is not equal to 0. This is the first condition. Now the second condition is a and b are co-primes. That is, the highest common factor of a and b must be equal to 1. So we have written square root of 3 plus square root of 7 equal to a by b. Now by rearranging this, we can write square root of 3 equal to a by b minus square root of 7. Now we square on both sides. Squaring on both sides, we get a square root of 3 whole square equal to a by b minus the square root of 7 whole square. Now we use the formula x minus y whole square equal to x square plus y square minus 2xy. By using this formula, we expand the right hand side term. A minus b square root of 7 whole square can be written as a by b whole square plus square root of 7 whole square minus 2 multiplied by a by b multiplied by square root of 7. Now we get 3 equal to a square by b square plus 7 minus 2 square root of 7 multiplied by a by b. We multiply by b square on both sides. 3 multiplied by b square on the left hand side term equal to each and every term on the right hand side must be multiplied by b square. So a square by b square is multiplied by b square plus 7 is multiplied by b square minus 2 root 7 a by b is also multiplied by b square. Now I bring root 7 theorem to the left hand side and all the remaining terms to the right hand side. By doing this, we get 2 root 7 ab equal to a square plus 7b square minus 4b 3b square. 7b square minus 3b square is equal to 4b square. So we can write square root of 7 equal to a square plus 4b square by 2ab. Now we apply mathematical logic to prove that a square plus 4b square by 2ab, that is the right hand side term of this equation, is a rational number. To prove this, we continue our argument, mathematical argument. A and b are integers. If a and b are integers, then a square is also an integer. B square is also an integer. That is, we are applying the properties of integers. If a is an integer, b is an integer, then a square is an integer, b square is an integer. We studied this in 6th class, 7th class, 8th class, and 9th classes. A square is an integer and b square is an integer implies 4b square is also an integer, because 4 multiplied by an integer is again an integer. 4b square is an integer. If these two numbers a square and 4b square are integers, then the sum of two integers is again an integer. A square plus 4b square is also an integer. So now the numerator part is proved to be an integer. Now we consider the denominator 2ab. We have to prove that the denominator is also an integer and it is not equal to 0. So to prove this, we write a is an integer, b is an integer. And in the starting, we consider that b is not equal to 0 and highest common factor of a and b equal to 1. This is because we assumed that a and b are two primes. So by all this, we get that a is not equal to 0. Why we get a is not equal to 0? We have mentioned that a and b have common factor, highest common factor equal to 1. If a is equal to 0, then we cannot get the highest factor, common factor equal to 1. So a should not be equal to 0. This is the condition. Now we prove that 2ab is also an integer and 2ab is not equal to 0. To prove this, we consider a is an integer, a not equal to 0. B is an integer and b not equal to 0. 2 is an integer, 2 not equal to 0. If by considering all this, it implies that the product of non-zero integers is again a non-zero integer. 2 is a non-zero integer, a is a non-zero integer, b is also non-zero integer. The product 2ab is also a non-zero integer. That means it can be written as 2ab is an integer and 2ab is not equal to 0. Now we can apply, that is, we have proved that the denominator part of the right hand side term is not equal to 0 and it is a rational number. It is an integer. So now we can apply the definition of a rational number. A square plus 4b square is an integer. That is, the numerator term of the right hand side is an integer. 2ab is an integer, 2ab not equal to 0. That is, the right hand side term denominator. Denominator is also an integer and is not equal to 0. So when these three conditions are satisfied, then we say that a square plus 4b square by 2ab is a rational number. This is by the definition p by q is an integer. The number p by q is an integer where p and q are integers. Q is not equal to 0. This is the definition of irrational number. Now we applied these properties to a square plus 4b by 4b square by 2ab. So since the conditions of a rational number are satisfied, we conclude that this is a rational number. When the right hand side term a square plus 4b square by 2ab is a rational number, we can conclude that the left hand side term square root of 7 is also a rational number. That is, we got that square root of 7 is a rational number. But in the earlier classes, in the previous classes, we have already proved that square root of 7 is an irrational number. We know how to prove this, how to prove that square root of 7 is an irrational number. We know that. We have already proved that. So we got a contradiction to the fact that square root of 7 is a irrational number. We got here that the square root of 7 is a rational number, but it is actually irrational number. This contradiction has arisen because of a wrong assumption that square root of 3 plus square root of 7 is a rational number. This is the wrong assumption. So, since it is a wrong assumption, square root of 3 plus square root of 7 is not a rational number. So, if this is not a rational number, then now we discuss the definition of an irrational number. What is the definition of an irrational number? A real number which is not a rational number is called an irrational number. Hence, we conclude that square root of 3 plus square root of 7 is an irrational number. Now, we solve another problem. 3 plus, prove that 3 plus 2 square root of 5 is irrational. Dear students, you must remember all these concepts are very, very important from the examination point of view for class 10. So, you must concentrate on this topic. You should learn by practice. Then only you will be able to answer to these questions confidently in the examination. We prove this result by contradiction method. So, we write it. We prove that 3 plus 2 square root of 5 is irrational by contradiction method. In contradiction method, we assume that the given statement is wrong. When we assume that the given statement is wrong, it implies that 3 plus 2 square root of 5 is not irrational. 3 plus 2 square root of 5 is not irrational means it is a rational number. So we assume that 3 plus 2 square root of 5 is a rational number, is a rational number such that such that 3 plus 2 square root of 5 equal to a by b. A by b, where where condition 1, a and b are integers and b is not equal to 0. This is condition 1. We must assume that a and b are integers and the denominator b is not equal to 0. Now the second condition. This is the first condition. Now the second condition. A and b are co-primes. Are co-primes. Then what is the definition of co-primes? Two numbers a and b, two positive integers a and b are said to be co-primes if the highest common factor of a and b is 1. So now we write the definition. Highest common factor of a and b equal to 1. So these two conditions are satisfied by a and b. So we assumed here that 3 plus 2 square root of 5 equal to a by b. Now by rearranging this, we get 3 plus 2 square root of 5 equal to a by b implies 2 square root of 5 equal to a by b minus 3. A by b minus 3. So this is equal to 2 square root of 5 equal to a minus 3b by b. From this we can write square root of 5 equal to a minus 3b divided by 2b. Now we apply the mathematical logic to prove that the right hand side term a minus 3b divided by 2b is a rational number. So we now write a is an integer, b is an integer. This implies that a is an integer and 3b is an integer. How can you say that 3b is an integer? 3 is an integer and b is an integer. Hence, the product of two integers is again an integer. If this is the fact, the difference of two integers is again an integer. So a is an integer, 3b is an integer. It implies that a minus 3b is also an integer. So this is very important. Now we have proved that the numerator of the right hand side term is an integer. We have proved this. Now we prove that the denominator term is 2b is an integer and it is not equal to 0. We prove that. So b is an integer, b is not equal to 0. That implies 2b is an integer and 2b is not equal to 0. This is why, because 2 is also an integer and 2 is not equal to 0. So from this we get the denominator 2b is an integer and it is a non-zero integer. We proved this. So from these two statements, that is the numerator is an integer, denominator is a non-zero integer, we get that a by a minus 3b. So hence hence a minus 3b by 2b is a rational number. That is, we proved that the right hand side term is a rational number. If the right hand side term is a rational number, then the left hand side term must be a rational number. So it implies that the left hand side term, what is the left hand side term? Square root of 5 equal to a minus 3b by 2b. So from this we got that the square root of 5 is a rational number. Square root of 5 is a rational number. This is what we got from the mathematical reasoning. Now, we have already proved that square root of 5 is an irrational number. We know this property. Square root of 5 is an irrational number. So now we write, but we know that square root of 5 is an irrational number. Square root of 5 is an irrational number. So what we can say is we got a contradiction. We got a contradiction to the fact that square root of 5 is an irrational number. So why this contradiction has arisen? This is the question. This is because of our wrong assumption. What is the assumption? So we assumed that. So now we write. Hence, our assumption. What is our assumption? We assumed that 3 plus 2 square root of 5 is a rational number. So this assumption is wrong. Wrong. Hence, our assumption that 3 plus 2 square root of 5 is a rational number is wrong. So if this assumption is wrong, then we can say that 3 plus 2 square root of 5 is not a rational number. Therefore, 3 plus 2 square root of 5 is not a rational number. So if it is not a rational number, then what will be the conclusion? Now we write the definition of an irrational number. What is the definition of an irrational number? A real number which is not a rational number is called an irrational number. So we write the step, we write this. A real number which is not a rational number is called an irrational number. Therefore, 3 plus 2 square root of 5, therefore 3 plus 2 square root of 5 is an irrational number. So we proved this result by contradiction method. We proved this result by contradiction method. Now let us discuss the problem. Prove that 3 plus 2 square root of 5 is irrational. Prove that 3 plus 2 square root of 5 is irrational. To prove this result, we follow contradiction method. Then, by contradiction method, we assume that the given statement is wrong. That is, we assume that 3 plus 2 square root of 5 is irrational is wrong. That is, we assume that 3 plus 2 square root of 5 is not irrational number. Not a irrational number. We assume that. So, as per our assumption, it is a rational number. 3 plus square root of 5, 3 plus 2 square root of 5 is a rational number such that it satisfies two conditions. 3 plus 2 square root of 5 is equal to a by b, where the first condition is a and b are integers, b is not equal to 0. A and B are integers, B is not equal to 0. The second condition is A and B are co-primes, that is highest common factor of A and B equal to 1. So now we consider this 3 plus 2 square root of 5 equal to A by B. By rearranging this, we get square root of 5 equal to A minus 3B by 2B. By rearranging this, we get square root of 5 equal to a minus 3b by 2b. Now we continue our mathematical argument. To prove that the right hand side term is a rational number. If we prove that this right hand side term a minus 3b is a rational number, then we get that square root of 5 is a rational number. But it is not the case. But square root of 5 is an irrational number. We got this contradiction just because of our wrong assumption. Now we continue our mathematical argument. A is an integer, B is an integer. This implies that A is an integer and 3b is an integer. Why 3b is an integer? 3 is an integer, b is an integer. The product of two integers is again an integer. So we are applying the product of the properties of integers. 3b is an integer. If a is an integer and 3b is an integer, then the difference of two integers is again an integer. We know this property. The difference of two integers is again an integer, and hence a minus 3b is also an integer. So we proved that the numerator term a minus 3b is an integer. Now we consider the denominator term 2b, and we prove that it is an integer and it is not equal to 0. So b is an integer and b is not equal to 0. This is because we assumed this. 2 is an integer and 2 is not equal to 0. From this, the product of two integers, the product of two non-zero integers is again a non-zero integer. I repeat this. Here we have to learn the properties of integers. If we consider two non-zero integers, then the product of two non-zero integers is again a non-zero integer. So here 2b is a non-zero integer. That is, we can write 2b is an integer and it is not equal to 0. Now we can apply the definition of an irrational number. What is the definition of, we apply the definition of a rational number. A number p by q is a rational number where p and q are integers and q is not equal to 0. So this is the definition of a rational number. By applying the definition of a rational number, we can conclude that a minus 3b by 2b is a rational number. So by our mathematical argument, we proved that the right hand side term is a rational number. If the right hand side term a minus 3b by 2b is a rational number, then we can conclude that the left hand side term square root of 5 is a rational. So we got this from our mathematical argument. But we know that square root of 5 is an irrational number. We know this fact. We have already proved the result. We proved that square root of 5 is an irrational number. We have proved that. Square root of 5 is an irrational number. So we got this contradiction because of a wrong assumption. Hence our assumption that 3 plus 2 square root of 5 is a rational number is wrong. Our assumption is wrong. So if our assumption is wrong, then we can conclude that 3 plus 2 square root of 5 is not a rational number. If this is not a rational number, then what will be the conclusion? A real number which is not a rational number is called an irrational number. This is the definition of an irrational number. So we conclude that 3 plus 2 square root of 5 is an irrational number. We proved this result by contradiction method. prove the now we consider the next problem. Prove that prove that square root of p is a is an irrational is an irrational number where p is a positive is a positive prime number. So this is very important result. We have already learned how to prove this. We prove this result by contradiction method. Suppose that p is a positive prime number. We prove that we prove that square root of p is irrational is irrational by contradiction method. So by contradiction method we assume that the given statement is wrong. So if the given statement is wrong, then square root of p is not irrational. If square root of p is not irrational, then it should be a rational number. So we assume that square root of p is a rational number such that square root of p equal to a by b, where where condition 1, a and b are integers, b is not equal to 0. This is condition 1. Condition 2, a and b are co-primes. A and b are co-primes. So co-primes means the highest common factor of a and b must be equal to 1. So we write it, highest common factor of a and b equal to 1. So we assumed that square root of p equal to a by b, where a and b are integers, b is not equal to 0. That is the first condition. And the second condition, a and b are co-primes. That is the highest common factor of a and b equal to 1. Now, by rearranging this, square root of p equal to a by b. So a equal to square root of p multiplied by b. Squaring on this on both sides, squaring on both sides, squaring on both sides, we get squaring on both sides we get a square equal to square root of p b whole square, that equal to square root of p whole square b square equal to p b square. So finally we got a square equal to pb square. So this is the result we got. Here we applied the formula xy whole power m equal to x power m y power m. So here x equal to square root of p, y equal to b, and m equal to 2. So by using this formula, I have written this. So here a square equal to pb square. This implies pb square is divisible by p. Now we continue our mathematical argument from this. We got a square equal to pb square. So now we write pb square is divisible by p. This implies that, so when the right hand side term pb square is divisible by p, a square should also be divisible by p. So this implies that a square is divisible by p. That is what we have written is that is p divides a square. By theorem 1.6, by theorem 1.6, if p divides a square, then p divides a. So therefore, it implies that p divides so therefore we get that p divides a. If p divides a, then we can write this implies a equal to pc. We can write. We can consider some examples for this. So for example, if 5 is a prime number, if 5 divides 100, then 100 can be written as 5 multiplied by 20. So this is of the form A equal to PC form. Now we consider another example. 17 is a prime number. If 17 divides 510, then we can write 510 equal to 17 multiplied by 30. So that is, this is of the form A equal to PC. Students can understand the concept from considering these examples. So if P divides, if a prime number P divides a positive integer A, then A equal to PC, we can write it. Now squaring on both sides, A equal to PC, we can write for some integer C, we can write it. So now squaring on both sides, squaring on both sides, we get A square equal to PC whole square. So that is A square equal to P square C square. But we know that A square equal to PB square. But A square equal to PB square. So we have the result in the starting. So from this, in place of A square, I can write PB square. So from this, I can write PB square equal to P square C square. So on left cancellation, we get B square equal to PC square. From this, now, so this is P square equal to B square equal to PC square. The right hand side term, so here PC square is divisible by P. It is very clear. PC square is divisible by PC square divided by P. So we get a C square on cancellation. So it is very clear. So we can write PC square equal to is divisible by P. So from this, we can conclude that if the right hand side term is divisible by P, then the left hand side must also be divisible by P. If the right hand side is divisible by P, the left hand side is also divisible by P. So B square is divisible by P. That is P divides B square. Now we apply theorem 1.6. Theorem 1.6 states that If P divides a square, then P divides a. From this statement, we can conclude that this implies that P divides B. So now we got that. Now we got that P divides A and P divides B. So we got this result. We got that. We got that P divides both A and B. So it implies that P is a common factor. P is a common factor of A and B. So that means A and B have common factor P. So this is a contradiction to our assumption that A and B are co-primes. This is a contradiction to our assumption that A and B are co-primes. A and B are co-primes. So co-primes means the highest common factor of A and B equal to 1. So we got here common factor of A and B equal to P. We got it. Common factor of A and B equal to P. So this is a contradiction to our assumption that A and B are co-primes. This contradiction has arisen because of our wrong assumption. So what is our assumption? Square root of P is our assumption. Is a rational number is our assumption. Hence, our assumption that square root of P is a rational is false. That is wrong. So if this is not a rational number, then what is the conclusion? So if a square root of P is not a rational number, then it must be an irrational number. Now we write the definition of irrational number. A real number, a real number which is not a rational number, which is not a rational number, is called an irrational number. So we conclude that square root of p is an irrational number. Hence square root of p is irrational. Is irrational where p is a positive prime number. Positive prime number. So now we write that we have proved the result by contradiction method. We proved this result by contradiction method. Dear students, let us discuss this problem. Prove that square root of p is an irrational number where p is a positive prime number. Here it is given that p is a positive prime number, and we have to show that it is square root of p is an irrational number. To prove this result, we follow the contradiction method. By contradiction method, we assume that the given statement is wrong. That is, we assume that square root of p is not a rational number. Square root of p is not a rational number means it is a rational number. If square root of p is a rational number, then we can write it in the form of a by b, where a and b are integers and b is not equal to 0. And the second condition is the highest common factor of a and b equal to 1. That is, a and b are co-primes. So now we have written square root of p equal to a by b. By rearranging this, we get a equal to square root of p multiplied by b. Squaring on both sides, we get a square equal to pb square. Squaring on both sides, we get a square equal to pb square. Now, we start our mathematical argument. The right hand side term pb square is divisible by p. It is very clear. Here, pb square by p equal to b square. So, the right hand side term p square is divisible by p. So, it is a clear statement. If the right hand side term is divisible by p, then the left hand side must also be divisible by p. That is, p divides a square. If p divides a square, then by theorem 1.6, if p divides a square, then p divides a. So we get p divides a. If p divides a, then we can write a equal to pc for some integer c. To understand this, we consider a prime number 5, and if the prime number 5 divides 100, then we can write 100 equal to 5c, 5 multiplied by 20. So this is of the form a equal to pc. Now we consider another prime number 17. If 17 divides 310, 510, if 17 divides 510, then 510 equal to 17 multiplied by 30. So this is of the form a equal to pc. Here the prime number is 17. So If p divides a, then we can write a equal to pc for some integer. Squaring on both sides, we get a square equal to pc whole square, that equal to a square equal to p square multiplied by c square. But we know that a square equal to pb square. So from these two equations, that is a square equal to p square c square and a square equal to pb square, we can write pb square equal to p square c square. Pb square equal to p square c square. So on left cancellation we can get b square equal to pc square. So here we got b square equal to pc square. Now we start our mathematical argument. The right hand side pc square is divisible by p. It is very clear statement. The right hand side term pc square is divisible by p. So when the right hand side term is divisible by p, we can say that the left hand side term is also divisible by p. So what is the left hand side term? B square. B square is divisible by p. So we got p divides b square. Now we apply theorem 1.6. According to theorem 1.6, if a prime number p divides a square, then that prime number divides a. So from this theorem, we can write if p divides b square, then p divides b. This is the statement. So in the earlier case, we got p divides a. Now we got p divides b. So combining these two statements, we can write p divides both a and b. P divides both a and b. So if P divides both A and B, then we can say that P is a common factor of both A and B. P is a common factor of both A and B. If P is a common factor of both A and B, this is a contradiction statement to our assumption that A and B are co-primes. In the starting, we assumed that A and B are co-primes. That is, the highest common factor of A and B equal to 1. We got this contradictory statement because of our wrong assumption. That is, our assumption that the square root of p is a rational is false. If it is not a rational, then it must be an irrational number. So here we write it, square root of p, square root of p is not a rational number. If this is not a rational number, then it should be an irrational number. So we write the definition of an irrational number. A real number which is not a rational number is called an irrational number. A real number which is not a rational number is called an irrational number. Hence, square root of p is an irrational number where p is a positive prime number. Dear students, I will continue the next problems in tomorrow's session. In tomorrow's session, we do some problems like square root of p plus square root of q is irrational, and also we study the properties of irrational numbers. So students are advised to go through the concepts and you must have some knowledge, previous knowledge on this concepts. So you go through the concepts. We will meet tomorrow. Thank you all students. Thank you very much.